Good day, friends. Today we're going to discuss something called optical instruments. And if you think first about something like microscope and telescope, when you hear this word, it's pretty much good because it is exactly what we're going to study today. But before we study those things, first we need to study something called lenses in combination. Later on, you will see that in fact microscopes and telescopes are just combination of two lenses. I will not tell you yet what combination is this. Maybe it's two converging, maybe it's two diverging lenses, maybe it's diverging and converging, or opposite, first converging, then diverging, and so on. But yet, let's just understand the basic nature of lenses of any combination, okay? So, for example, if we imagine the situation, try to imagine like there is no any text right here, do not concentrate on that. Just look at this situation, You have first your object, which is right here. Then it spreads some light, it reflects some light, and then you have your converging lens, which collects light somewhere, and then you have your object, and it is inverted, or you have your image, I'm sorry. However, this text is really important to look at this one. Image of the first lens serves as the object for the second lens, So if this thing is the image for the first lens, it's the object for the second lens, okay? So when you work with the second lens, you don't concentrate on that, you just forget about it. Right now you have this part and you forget even about this lens. You're only interested in this object, which is the image for the first lens, and this diverging lens. Then you do just a simple rules of refraction, So as you can see here, this lens has its own focal point, which is this objective. So let's look at this text right now. Now we can concentrate on it. First lens, independent of its nature, is called objective. So it does not matter which lens it is. Is it diverging lens, converging lens? Maybe it's even planar convex, planar concave lenses. Maybe, just maybe, that it is some concave meniscus or convex meniscus. It does not matter, okay? That's why the first one is just called objective. The second one, independent of its nature as well, is called eyepiece. Okay, so we need to remember those things. As you can see, this converging lens has its own focal points. This one, and diverging lens has its own focal points. This one and this one. Okay, and one new value, which is L. Distance between two lenses is noted as L. So this thing is also important. We're going to discuss about it a little bit later. But right now, let's look at the formulas. So we have the basic formulas that we use. Generally, we have this formula, which you probably learned how to use in the very first videos about ray optics. Then you have simple magnification formula, and also maybe some new formula, but I hope that you know it from your school. This is the power, Some people write it with just a huge D, but I love to write it like this, DPTR, which means dioptry. Just 1 divided by F. This thing would be your power, and this is in dioptry. But one thing to note, if you write it in centimeters, then you have to write here 100 divided by F in centimeters. But if you want to apply meters, this thing stays 1, but you need to convert this thing. For example, if it is 30 centimeters, then you have to convert it into 0.3 meters. Okay, this is important. Okay, new formulas, which we are going to use is this equivalent focal point. So what is equivalent focal point? If you remember your electricity and magnetism courses and so on, then you definitely know something like equivalent resistance, equivalent capacitance, equivalent voltage. So it's not the average, but the total voltage, And the same thing goes for this one. It's the total focal length. If you have the focal length, the first, which is your objective, and then you have your second focal length, which is your eyepiece, and then you make minus L is the distance between two lenses, F1 multiplied F2, okay? However, it's only in that situation where you have distance between two objects. If there is two lenses, If your two lenses, for example, let's imagine this lens comes here and sticks to it, like this one. For example, these are still two lenses which are stick to one another. In that situation, this L is going to be 0 because there is no distance between two lenses. That's why this whole side will be just 0. So what you will be left with is F equivalent equals F1, 1 divided by F1 plus 1 divided by F2. Okay. The total magnification looks like this. You just multiply the first magnification and the second magnification. You can open this formula by its own formula, which is minus DIDO, and you can put it here. And these two minuses will be just positives, and it will be the same thing as the image 1 divided by the object 1 multiplied the image 2 divided by the object 2. Okay, so or otherwise we can apply the formula of heights. these four don't have to be the same. Yeah, these four don't have to be the same, even though some people might think, well, distance of the first image is the same as the distance of the second object. No, it's not so. For example, if you look at this, this is our distance of object 1, right? This is our distance of image 1. This is image 1. As you can see here, it's four blocks. 4 blocks. Yep. This one, this one, this one, and this one. Okay. And even though it is the object for the second lens, you can see here that this distance is 6 boxes. 6 blocks. Yeah. So 1, 2, 3, 4, 5, 6. You can definitely see it. So that's why DI1 is not equal to DO2. Yeah. It can be, but it does not have to be, okay? It does not have to be. When we deal with heights, it's a little bit more interesting. We open the magnification formula by height of the image 1, height of the object 1, multiplied height of the image 2, divided by height of the object 2. Now we can cancel these two things, because no matter what we do, this height is height of what? This is the height of the image 1, right? At the same time, this thing is the height of the object 2. That's why those two things are equal to each other. They are the same. And that's why we can cancel those out, and then we will be left with height of the image 2 divided by height of the object 1, which means this is the last height of the last image, and this is the initial height of the initial image, right? Initial object, yeah, sorry. Okay. This is a little bit more interesting concept. It's pretty, here we can understand two things. I did not explain it after this one, because right now, we're going to understand and learn two new things. So, we did not just take this thing and flip with this converging lens. We did not change their places only, yeah? Here we have a little bit different, yeah? If you look at this situation, it was very simple. You have converging lens, focal point, diverging lens, focal point, yeah? So it's not much of a deal, in fact. There is nothing complex. But in this situation, you can see something and learn something. New thing that you're going to learn. You draw the simple image formation by spherical lenses, yeah? You do ray tracing, which is pretty much easy. You get your first object, first image. But if this thing is the object for your second lens, right? If this is the object for your second lens, then it must emit some light and go to the converging lens. But you see that first, before it reaches this place, it hits the diverging lens again. And will it be refracted? Yeah, will it be refracted like this one, and so on? No, it will not be. So this is something new for you to learn. When we have some object, it does not matter to work with first lens again. We just cancel this out. The same thing, we cancel this object out. We're not interested in them. What we are interested in is this object and this lens. That's why you imagine like this diverging lens just disappeared, okay? It pierces through, and then it collects light somewhere here. Then you will have your image, final image somewhere here, okay? The second thing that you're going to learn right now, look at how their focal lenses are placed. Focal length of the first diverging lens, it is here and here. Yeah. The focal length of the second lens, which is the eyepiece, it is here and here. So you can see that the focal length of the this converging lens is closer to diverging lens. Yeah, this is this distance is closer than its own focal point. Yeah, this is focal point. This is the focal point of its own. However, its focal point is closer to this diverging lens, and it's pretty much okay. Yeah, you can see here 3 boxes. Right now it's also 3 boxes, but still this eyepiece is 1 box closer to diverging lens. If we move this converging lens probably here, like 2 boxes, then definitely it must move where? It must move somewhere here. So our focal point would be somewhere here. It's possible sometimes when our focal point of the eyepiece might be inside of the diverging lens, or inside of the focal point of the diverging lens might appear inside of the converging lens. There are such kind of situations. It's okay. You just deal with it as usual. Okay? Good. Right now, we can go to telescopes and microscopes. Yeah? Now we're allowed to study it. So as you can see, as I have said before, this is the combination of 2 lenses, right? And you can see it clearly that both of them is a combination of converging lenses. There is no any diverging lens, only converging lenses. Okay, good. So telescopes, the main principle is like this. 2 converging lenses with large focal point for the objective and small focal point for eyepiece. So the first lens has to be larger, its focal point must be far, and its focal point of the eyepiece must be not that far. It must be a little bit close compared to the objective. Okay. You can see that light is approaching with a certain angle like theta object, because we work with objective lens first. And then we know that the line which passes through the center, it does not bend. And if this angle is theta, then this angle is the same. Yeah. Okay. The same thing goes for eyepiece. For example, here we have different angle theta I, and the central line does not bend. That's why this angle has to be equal to this angle. Okay, this will be important to us a little bit later, but right now let's look at different things. Well, this is our L, yeah, as usual. Well, not much interesting, but what is interesting is this thing. Look at this one. This is the focal point of the objective. This is the focal point of the eyepiece. And what you can see is that those two are exactly this length. So right now you have one more new formula, which is L equals F objective plus F eyepiece. But it works only for telescopes. This works for telescopes. Yeah, you need to remember this. What about the objective? Theta objective, it's minus HI divided by F objective. Yeah, okay, minus HI divided by objective. For example, let's imagine that here we have something large. Basically, with telescopes, we try to see something very large, maybe something like Milky Way galaxy, Andromeda galaxy, or something like that. And we need to shrink this thing. Our galaxy has to become something very, very small, in fact, to see it. Okay. So it was seen by our eyeball. Yeah. So we have some minus HI divided by F objective. What is that thing? Minus HI. Yeah. This is theta objective is this angle, as you can see. Yeah, objective. We can apply here small angle approximation, which is sine theta will be equal to theta, but it will also be equal to tangent theta. Yeah. If it is tangent theta, then definitely tangent is opposite divided by adjacent. Our opposite is this, is our height of the image, which is inverted. That's why it will be minus. And adjacent would be this distance, which is the focal point of the objective lens. Yeah. So that's why we have this kind of formula, which is theta objective minus HI divided by F objective. Yeah, F objective, it's adjacent. This is opposite, and minus comes from HI because it is inverted. What about the eyepiece? What's the problem with eyepiece? Eyepiece, as you can see here, it will not be inverted. Why? Because the final image that we will see, we will accept. As I have told you before, our brain loves imaginations. It will seem to us that our object will stand somewhere here. Yeah. It will continue the imagination, and that's why your image at the end would be still inverted. That's why this thing will not be minus. HO, yeah, because this thing would be right now object, yeah. This is opposite divided by adjacent as well. Adjacent is this focal length of the eyepiece, yeah, and that's how you get this formula. So for telescopes, just for telescopes, magnification will be theta eyepiece divided by theta objective, yeah, the ratio between two angles. And you can apply here those formulas, which is this one and this one. As you can see here, we put them here, and then don't forget the minus. Minus is right here; it stays. HI is cancelled with HO. Why? Because it's the same object. This is the height of the image for first lens, but this one is height of the object of the second lens, right? So that's why those two values are equal to each other. At the end, we have something like minus F objective divided by F eyepiece. Okay. What about the microscopes? It's still two converging lenses. It's still two converging lenses. It cannot be otherwise. With small focal length for objective and large focal length for eyepiece. Okay, so this one eyepiece has to have larger focal length. As you can see here, it's a little bit far than this one. This is pretty close. Yeah. This is our objective because, as we have said, independent of its nature, the first lens which accepts light will be our objective. The second one will be our eyepiece. It does not matter about their size. It does not matter about its nature, and so on. One more interesting thing that you see here. This is the total lens, and focal point just ends here. For this one, focal point ends here. Can you see how much of empty space we have here? This one, which means that our L will not be equal to these two. Okay, so remember this thing for microscopes, L is not equal to F objective plus F eyepiece. There is a distance between them. But we can say that lens is the length of the tube. So tube is just a shell that makes those two keep distance, yeah? Keep a certain distance, and that is the shell inside of the microscope. And that would be exactly the length of the distance between two lenses. If in the problems you are set that the length of the tube of the microscope is such, then you definitely know what it is. It's the distance between two lenses, okay? And magnification goes by the main formula that we have mentioned in the beginning. the first magnification multiplied second magnification, yeah, and one is objective, the second is eyepiece. Okay, okay. The same thing. Our brain loves to imagine it further. It gets something like this. So our image would appear somewhere there. Okay, you can see here it's the very small object, maybe some kind of bacteria, and then we enlarge it, as you can see. And image is real still. Yeah. So image is real. It is enlarged several times, and then we can see this bacteria as being enlarged, but in fact it's still small. Yeah. Okay, good, good. The next thing that we are going to study about is vision, or better to say glasses. Yeah. And so let's talk about the normal vision. So basically, normal human being has such kind of eyeball. Yeah. It is not perfect circle, but it reminds something about the perfect circle. That's why we will write it as this one. Yeah. So interesting fact about our eyes is this kind of. So our eyes play the role of converging lens. If you have light rays approaching your eye, then it collects light in here, which is your optic nerve. Your optic nerve receives the information in the form of light and then converts it to the information that is available to our brain, which is understandable to our brain. Yeah? Okay, good. Then, some interesting facts about the normal vision. Eye acts like converging lens. We have already mentioned it. Two more things. 25 centimeter is the smallest distance to see well-focused image for a normal relaxed eye. What does it mean? It means that if you have a normal vision, if your vision is okay, yeah, is usual, yeah, then you cannot concentrate on something closer than 25 centimeters with relaxed eye. You can do it, of course, but not with a relaxed eye. If you can concentrate on 5 centimeters, then it's okay. Yeah, it's not some problem. You can concentrate, you can focus on something which stands 5 or maybe 3 centimeters in front of your eye. However, the problem is you do it with not relaxed eye. You make some pressure on your eyes. Yeah. Then the farthest point at which I can focus is infinity. Yeah. Well, this statement is a little bit debatable, but scientists use this principle and it works pretty good. That's why we will continue with this principle as well. The farthest point is not some kind of 10 kilometers, 20 kilometers, and so on. In fact, it is infinity. Okay, good. Sometimes we might have some kind of defects, and one of them is present in my situation. It's myopia. I have this defect, and maybe you have this defect. Hyperopia mostly is met in older generation. Yeah. So this thing maybe explains everything pretty well. Far objects are blurry, so which means that you have a problems with far sight. You cannot see pretty good from very distant, very large distances, right? Hyperopia is opposite. You cannot see pretty good near objects. If you have noticed your grandfathers, your grandmothers to hold their books or smartphones away from themselves, then it is not that some sort of a habit. No, instead, it is because they have this kind of defect, which is called hyperopia. They cannot see very well from near. Okay, there are ways to correct it, but as you can see, let me show it closer. What's the problem? The problem is that light still is collected at the same point. In the very beginning, you had normal eyeball, and it's okay. Sometimes this kind of eyeball, it enlarges. For example, in my situation, because I had a good vision, and growing up, I messed it up. Okay, and light still converges at this point. However, its continuation is here, and then I see this kind of image which is blurry. But I want this point will be focused, and I want to move it here. Okay, the same thing happens for myopia. In the beginning, maybe your eyeball was this kind of, and then it shrinked, and you still collect light here, even though your optic nerve is here. You want to collect it at this point. Yeah, there are ways to correct it, and for myopia, you need diverging lens. Yeah, some lines approach the diverging lens, then it spreads away, and then these lines are collected a little bit far, and right now it is exactly at your optic nerve, and that's how you see things very clearly. That is our glass. Yeah, the same thing goes for myopia, but instead you put here converging lens because you need to collect light 2 times. First it approaches converging lens, then it collects light, and then it collects again 2 times. That's how your image becomes clear at this point. Okay, good. To treat myopia, yeah, we want person to see well as far as normal vision. Yeah. So as we have said, myopia is when I can see pretty good from close, but I cannot see pretty good from far, and I want to see from far. If you have a question why, for example, let's imagine the situation in cinema. I go to cinema, and I have a ticket on the last place, and when I watch movie, the movie is very blurry, right? It's not because of the resolution of this image. It's not the problem with cinema itself. It's the problem with my vision. And I want to correct it. I want to be able to see the movie clearly. Yeah, that's why I want to learn how to see things as far as a normal vision. What about the hyperopia? To treat hyperopia, we want person to see well as near as normal person. So the thing is, they want, these people who have hyperopia, they want to see as close as a normal person. Yeah, as I have said, they cannot see close, but they can see, but it will be very blurry, right? And they want things to be able to be seen clearly from near. Yeah, why? Because maybe it's not comfortable to hold the book from 1 meter all the time. You want just hold the book as usual. That's why you want to correct your eyesight, right? And to correct it, we use here diverging lens. We use here converging lens. Yeah. So the thing is, to correct myopia, yeah, we need to use this thing: 1 divided by f equals 1 divided by infinity minus 1 divided by di. Well, this is not something new. It's the usual formula, which is 1 divided by f equals 1 divided by do plus 1 divided by di. But there are several problems. Well, this part is okay. Yeah, focal point, that's okay. Only thing that is not okay, it's this infinity. Also, we have one more problem, is that this is minus. Yeah, because in original formula it was plus. The idea is the same for hyperopia, but instead of infinity, we put here 0.25. Or in centimeters, it would be just 25 centimeters, okay? Okay. The question is why both of them are minus. Because the image is virtual. When we create something like this, in fact, what happens is that we collect light somewhere here. Yeah. Right now, we collect light somewhere here. The same thing happens here. The not true lines continue, and you see it like here. Okay. That's why these are virtual lines, not real lines. It would be minus di. This would be minus di because it's virtual nature. What about 1 divided by infinity and 1 divided by 25, 0.25? And as we have said already, if myopia wants to see as far and the maximum far is infinity, then of course this thing would be infinity. If hyperopia, people who have hyperopia, they want to see near as possible as normal human being, then it must be 25 centimeters, not closer, because normal human being sees very good from 25 centimeters with relaxed eye. It's here, yeah? And the question is next, why these two do not change places? Why it's not infinity and this is not just do? Why it's not just do and this is 0.25, yeah, or 25 centimeters? The question is, I want to ask you, do you see objects or their image? Yeah, and that is the question. So, in fact, we need to think about it every time when I interact with something. In fact, I interact with the object. But do I see the object? No, I see its image that is projected in my brain, right? So I want my image to be clear, to be focused in very far distance, yeah? So this will be infinity because at any distance, my object, I want to see clearly objects at any distance, which is this one, yeah? So object does not change its place. It will be as maximum, it's infinity. But the image must appear somewhere else, okay? The same thing happens to be here. This thing would be 25, not this one. Why? Because I want my object, my image to be focused, yeah, focused at this point, at this point, okay, yeah? So I'm concentrated on my image, not the object. And let's try to solve two more problems that maybe just will help you to understand this this idea even better. Yeah. So we have here what? Martina has myopia. The far point of her left eye is 200 centimeters. What prescription lens will restore normal vision? Okay, let's concentrate on this one. So you have a girl, Martina, who has myopia, which means that she cannot see good from far, and her far point of her left eye is this 2 meters. Yeah. So what is the model? Model is like this. Normal vision will allow Martina to focus on a very distant object. Okay. Then we need to find prescription of lens, which means that what kind of characteristics, yeah? If you remember, if you ask your friends what lens prescription they have, then they would answer something like +3, -2.5, and so on and so on. We need to find the power of the lens, in fact. Okay. First, we need to calculate the focal point, which is found by this formula, 1 divided by f, and we want Martina to be able to see very far distant things, yeah? So that's why we would put her object at infinity, yeah? This thing would be infinity, minus 1 divided by di is her 200 centimeters, which is here. And then you definitely know that 1 divided by infinity gives us 0, and then you would have this kind of answer, which is 1 divided by f equals 1 divided by 200. And then your f would be equal to minus 200. You apply here the power formula, which is 1 divided by f. And here, as I have told you in the very beginning, we need to work with meters or the centimeters. If it is centimeters, we apply here just 100. If it is meters, it's just like this. So let's convert it into meters. This is centimeters. This thing would be minus 2 meters. And this thing would be minus 1 divided by 2, which is minus 0.5 dioptries, dptr, or somebody writes it as d, large d, yeah? I love to write it as this one. So, in fact, not that much of a problem. As you can see, the lens prescription that she needs is just minus 0.5 dioptries, yeah? Okay, good. And which is good. This must be minus, which means that this is the diverging lens, and this idea is proved. We need diverging lens to correct myopia. Yeah. For correcting hyperopia, we expect the thing to be converging lens. That's why we expect at the end the positive answer. So Sanjay has hyperopia. The near point of his left eye is 150 centimeters. What prescription of lens will restore normal vision? Yeah. So this one is his DI. The model is next. Normal vision will allow Sanjay to focus on object 25 centimeter away. Maybe Sanjay has a problem with reading books. He has to hold books at 150 centimeters to see it clearly. And he wants to hold it as a normal human being at 25 centimeters distance. Yeah. So that's how we put here that formula. The same formula like this one, but a little bit different. So I write it here. It would be 1 divided by f equals 1 divided by 0.25, or in centimeters just 25, minus 1 divided by di would be 150, because minus because it's virtual image, right? So if we give the common factor, this thing would be 150 still, this would be 6 minus 1, this thing would be 5 divided by 150. We cancel those two out, this thing would be 1 divided by 30, yeah, and our focal point would be 30 centimeters. It's positive and it works. And in terms of meter, it would be 0.3 meters. Okay. So if we want to find the power of the lens, the prescription of it, this would be 1 divided by focal length, which is 1 divided by 0.3. And this gives us something about positive 3.3. Yeah. dptr dioptries. Okay. Which means that to correct his eyesight, he needs the positive prescription lens, and this is our converging lens. Okay, I hope that it was clear to you. If it was not, you can write me privately. Thanks for your attention. Goodbye.